Hello everyone and welcome back. In the previous video we created a bolted plate connection and performed a basic structure analysis using ANSYS. Now we are going to take the next step and discuss how bolted joints are evaluated according to the VDI 2230 guidelines. When engineers design a bolted joint, it's not enough to simply check stresses in the surrounding structure. The bolt itself must also be evaluated properly. That includes checking bolt preload, clamp force, safety against yielding, joint separation, fatigue behavior. So VDI 2230 provides a systematic method for performing these calculations. I'm gonna to show you in this video how to perform this evaluation using two methods. The first one, it's a simplified way, just to check if the use bolt size were okay or not. And let's do this together. Now, from the analysis we did before in the earlier video, we already have the bolt pretension, which is the reduced bolt pretension for this bolt size. Actually, this M8 bolt size could be with a bolt pretension of about 18.6 kilonewton. But in this analysis, we only defined with 10 kilonewton as a bolt pretension. And from this analysis, what's important or what you have to get from this analysis to check the bolt actually is the shear force acting on the bolt. And clicking on the shear force, as you can see, we got around 7.4 newton as a maximum shear force. So let's write this alongside. So shear force, we get around 7.4. So let's make it 8 newton to be conservative. So 18 newton just as a shear force acting on this bolt. Now, in order for the next step, we need to know the axial force acting on the bolt, but without defining the bolt pretension. So in order to do this, you go back to the workbench schematic, you duplicate this analysis and initiate the simulation again, but without bolt pretension. So I will show you in this video simply how to do this. I already did this, so I will show you in steps how this could be done. So after duplicating this analysis, you will get a new analysis. You open this analysis, and what you have to do is you have to suppress all this bolt pretension by clicking on them and click on suppress. And because you suppress the bolt pretension, so no need anymore to define two-step in the analysis settings. So you can go back to the analysis settings and define just one step instead of two. And you don't have to forget that to go to force and move the 1000 newton to the first step. So like this, the analysis will be ready. And after you defined or the boundary condition like this, you go to the solution and solve the problem. So after you solve the problem, all what you need from this new analysis actually is to go and check the axial force acting on the bolt, which are the external axial force. And from this analysis, and as you can see here, we have around 416 newton or 417 newton acting on the bolt. So let's write this side, axial force on this bolt is 417 newton. Now let's go further and see according to the VDI guidelines if the chosen M8 bolt were okay or not. So from the guideline itself, we have the following. You can see on the screen to the left, we have this table and the conditions or the approach how to use this table. So first of all, we have to check one condition. So if the shear stress divided by the frictional coefficient greater than the axial force, then the shear force will govern and it will be the force used in the table. And if it's vice versa, if the axial force is still greater than this force divided by the frictional coefficient, then the axial force is to be selected. So let's do an example together. So alongside here, so we have to check first of all the 80 Newton, the shear force divided by the frictional coefficient. In our case it was like 0.12, and out of this formula we got the following. So 8 divided by 0.12, so I get around 67. So let's write here 67 Newton. So now we compare this value to the axial force, and as you can see it's still actually much lower than the axial force. That's mean we should use the axial force in the table to see if the bolt size is okay or not. But this is not everything. We still have to check two things. First of all, we should to check the load type, if it was like static or dynamic, or it was like concentric or eccentric, and how was the tightening method defined in this model. So if you go to the description on this page, you will see that our option could be the dynamic concentric way or option, or the static concentric type here. Of course, the worst case it could be the dynamic one. So for the dynamic concentric load type, we should move one step further. So this is the first step. Now we go and check the tightening method used in the model. It's already unknown in our model, so to be like conservative and as a moderate option, let's go and take the one step, which is the moderate tightening using a wrench or precision like spindle. So it's about like one step. So now in total we have to move or use two steps in addition to the force we had before in the table. So how to do this? Now as axial force we had 470 Newton, and this actually lies between the 400 and the 630. So we choose always the next like limit, which is the 630 in our case, and I should to move two steps, as we talked before about the load type and tightening method. So we are lying at M3 8.8. So that's mean the M8 8.8 chosen in our system were like way bigger, like for the minimum allowing like bolt size according to the VDI. This is a very simplified way to check if the bolt size were okay or not, satisfied according or under the load like defining on our system. We only had like 1000 Newton as a vertical force acting on the top plate, which is like not too much for this 4 M8 bolts, but according to VDI with this simplified way, we are sure now that the bolts are okay. This is the simplest way to check the bolts. Now I will show you the second approach and to see like a number, like how much safety factor we have against yielding for this bolt size according to the VDI 2230 guideline. So to do this, we need to know the following. We still need to know the external force acting on the bolt, which is actually from the analysis without bolt pretension, and in our case it was around 470 Newton. I will go now and show you in an Excel file I already prepared, like according to the VDI guidelines, how the bolts are good actually. So in our case, in the first analysis, we choose a bolt pretension of 10,000 kilonewton, and I type it on this cell here, 10,000 Newton. Now, from the analysis without bolt pretension, we got the external axial force 470 Newton, and from the VDI guidelines, I got a load factor of 0.15, which is the factor coming from the formula of the stiffness of the bolt and the stiffness of the connecting plate. You can see this in details in the VDI guidelines. Of course, if you have like any questions or further, or you want to discuss this, you can like write on the comment and I can like discuss with you that personally. in details, but for now, out of the guidelines, I got like 0.15. That's mean from the 417 Newton, only 15% will go to the bolt and the rest will go to the plate connection. That's mean 15% of this value, it will be like about 62 Newton, and this will be expected to be added to the bolt pretension, which was 10,000 Newton. And now in total we have around 10,063 Newton. This value I tip it as FS max 10,063 Newton, and out of this value I expect to get how much stress will be on the bolt itself. And from the analytical calculation, as you can see now, and according to the cross-sectional area that we have here, the 36.6, we are assuming, or we are expected to have around 275 megapascal. So let's check if this analytical calculation it's like match the simulation. I will go back to the simulation with bolt pretension, and when in this analysis we already like created a stress evaluation on the beam itself. And as you can see right now, if I go and take a probe and check the stresses in the bolt, we are right having about 275 megapascal, and that's now make like as or validate our analytical calculation alongside. So we are expecting 275 megapascal. But this not all actually. Okay, this is right for now, but it's still one step missing. So let's go back to the table. So it's okay, it's right that we have only 275 megapascal on the bolt, but we still have extra stresses coming from the tightening of this bolt. So according to this analytical calculation, and for this reduced bolt pretension, which is the 10,000 Newton, I expect to have around 131 megapascal from the tightening. So from this now, both stresses, the total von Mises stresses will be or the sigma will be calculated from this both like the tau and the sigma stresses. We get as a final stress acting on the bolt of around 297, and this what the simulation not showing us, because the tightening factor it's like an extra load that will be act on the bolt actually. So this is the final stress acting on the bolt, and now comparing this to the yield strength of the bolt used in our model, which was with a grade strength of 8.8. That's mean we have a yield strength of about 640 megapascal. We got as a final safety factor of about 2.15. That's mean from that simplified way we got the answer if the bolt are enough like big or not from this table or this approach. And if we need like a further detail like safety to know the safety factor against yielding, for example, according to this analytical calculation, which is like based on the VDI 2230 guidelines, we got an approximately like value of around 2.15 as a safety factor against yielding. So this is the second method, which we will get like more details about your bolt. I can show you right now also the second one and the final check against shearing eigenclash. And to do this, we can do the following. So to check the safety factor against like shear, for this bolt, we could use according to VDI the following the following formula, which is that the tau actually, which is the ultimate strength of the material, which is 800 megapascal, multiplied by a factor of 0.65, and this factor is only relevant to the bolt with a grade strength of 8.8, divided by the shear force that we have, which is like low in our case, so we are expecting to have like a so high safety factor. But let's do it just as an example for now. So we have 80 Newton as a shear force divided by the cross-sectional area of this chosen bolt, which is 36.6 millimeters square. And out of this formula you will get actually the safety factor for this bolt against shearing. So let's calculate this together. So for now, 800 times 0.65, so I have 520. It will be divided by 8 divided by 36.6, so I got 0.2186. And the final answer, so the safety factor against shearing, will be the 520 divided by 0.2186. So we have like a huge like safety factor against shearing because the shear force is like nothing. We got like around 2378 as a safety factor, but it's too huge. Like in case you have like much higher like shear force, like for example 500 Newton instead of 8, so you will get with 500, you will get 500 divided by 33.6, you will get 13.66, and we should have 520. Out of this we got around 38, which is like much reasonable in this case. But in our model we don't the bolts are not like against shearing overloaded actually, so they are like only only under like axial loaded. So of course we got like a huge safety factor against shearing. So like this, we got the safety factor until now. We got the safety factor against yielding, safety factor against shearing, and we already learned how to check the bolt in a simplified way according to the VDI guidelines. A small verification of the clamping like force like on our model for now, it's in this analysis. So as we saw like before, as a total expected force on the bolt, it will be around 10,063 Newton, and as a minimum from here I'm expecting to have a clamping force in the two plates of around 1040 Newton, which is like enough for the plate we have. Of course, when you are like have higher and higher like axial force acting on the bolt, the clamping force, as we learned before, it will decreases. So I hope this was clear in this video. If you have any questions, you can write on the comment and contact me if you have like any projects to be discussed or to be evaluated according to VDI guidelines, like we can do it. And for now, and in the next video we will go like further into like a practical bolt calculations and look like how to estimate preload, bolt force and safety factors step by step. So for now, if you found this helpful, make sure to subscribe so you don't miss the next part of the series, and feel free to leave a comment if you have any questions or topics you would like me to cover. So thanks for watching, and I will see you in the next video.